At least in my opinion, I think we should work only 4 days a week. No? So to work like 6 days a week would be heavy, 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 heavy. And going to school, you should only go for 4 days a week. That would be the optimum working days and studying days, right? And maybe 3 days even better. But yeah, I have to say, if you go to work for 4 days, that would probably you will get the optimum say output from your workers, right? Instead of trying to go for more days and become less productive. Can we start now? I think we ready, right? Okay, so I'm just gonna get going. Okay. Today actually we have more slides because it's about the connections now. I have to say, compared to compression members and flexural members, the design and calculation of connections is easier in terms of the calculation itself. But the problem with the connection is always we don't have enough reading materials. And we don't have enough time in the undergraduate level class to study about it. Normally, two things. I had a class about connection in a graduate level, and even with one class, my advisor could not cover everything. And second of all, if you look at the specification from AISC, generally it is free to download. But its specification will contain only fundamental ideas about the calculation and the failure of the connection. But for the design of the connection itself, how do you need to check on things? They are not listed in the spec itself. It is always included in the design manual, the steel design manual of AISC. Now the spec is free and the spec is part of the design manual. But the design manual itself is not free. We're going to have to try to find a way to buy it. And generally, it's not available in Thai market. So if you really want to buy it, it's going to cost you some fortune. So I remember looking at some website of the bookstore, and they say it's available for you to order, but they're in turn going to order from somebody from abroad. So it could cost like more than 10,000 for the manual. I remember I asked one of my students who went to the US for his master's to just buy one for me and just carry it back for me, and it cost me like 7,000. The 2010 manual. So for the 2015, I don't have a means to buy it yet. So if any of you want to go and have some further education in the US, please let me know. I'm going to ask you to buy it for me. But I'll pay for it, of course. Okay, so let's get started. Okay, like I said, the design itself is not difficult. The basic idea about the design of the connection is that, of course, the type of the connection should depend on the force that we need to transfer. So if we need to transfer the axial force, it becomes the axial force connection. And if you need to transfer the shear in the simple beam, it becomes a shear connection. Okay, and if you need to have the fixed end support, you're going to have the moment connection, just like that. And of course, the next important thing is the type of connection will invariably affect the construction cost. A general idea about this is that we should never try to weld in the field. The general idea is that you should always try to weld the piece of metal together in the fabrication shop alone, because that's where it is most safe. All right, and you can control the quality. And in the field, you should only try to use bolts so that the erection process can go very, very quickly and safely. But I have found this out, that the construction in Thailand, if it is a small job, generally the contractor will not have the fabrication shop, right? Only the big companies will have that. So the big companies can lay out a very good plan for fabrication. They could just prepare everything in their own yard, and then bring everything to the field and just connect it just like that. I have a good connection with a company down the road. You know that NL company. It's a very good company, and they have their own fabrication shop, and they love the boats very much because it makes everything fast, and they don't have to worry about the quality of the welding on site at all. But if the contractors are small companies, it's very hard for them to fabricate the piece of a structure and then have them shipped to the site. I remember a few years ago, because I did a small job for my friend, and I specifically say that, okay, you need to weld this and this and this first, and then you just, raise them up and then bolt it together. So when one day I paid a visit to my friend's place, and I was shocked because the contractor would just bolt everything on the ground and just lift everything and weld it, or just in the air, just like that. It's just, and then from that day I understood they did not have the way to measure and prepare the members to the very good detail. So they were afraid that the length of the member and the size will not fit. And welding will give them that kind of tolerance, because they could just lift the members up and just, okay, if it doesn't fit, we can just adjust the welding, weld it longer, weld it shorter, things like that. If you are going to use the bolts, you need to punch a hole first, right? And then if you punch a hole and then, oops, we just missed it by 1 inch, it would never fit. It was just that much. So it becomes an obstacle for some small scale contractors to follow the general ground rules for the construction of the connection. But if you could, it is much better, because it will go very, very, very fast. We can prepare everything. We can cut every member down to the details that we want, weld everything together, and when you bring your stuff on site, you just need to bolt them together. So it's going to be very quick and clean and fast and safe. Okay, and I already include the 3 items there, and that's it. Now the design concept. Generally, we need to know the strength of the materials that we use. Right? That's basic. And we need to know the type of forces that we're going to need to transfer, because that defines the type of the connection, right? And then we need to know how the load will travel. I generally speak this after my own advisor, so we call that load path. How the load will travel from one place to another, the path of the load. And then if we know our material, we know the force, we know how it travels, we know how each traveling can cause material to fail in which way, and we're just going to need to check all those corresponding failure modes, then that's it for the design of connection. And I don't know why I include that picture. That's one of the places that I used to be. It's a very famous steel structure building by the famous architect called Mies van der Rohe. He came from Germany. He used to be an engineer, and then one day he turned himself into an architect. But the idea of this crown hall is that he used the plate girder, but instead of supporting the roof itself, the roof is hung at the bottom flange to create the big space there. And of course, you bet there are no columns inside, just a 40-meter long span plate girder. He was the one who coiled the phrase "less is more," I think. But that doesn't apply to everything, right? Because if we have less money, we don't have more money. So it's sort of a minimalist approach. Anyway, so if we look at something complicated like this, but we understand how the load will travel from place to place, it's not that difficult. For example, this can be part of the truss in the old days details. So you know that this member probably carries the axial force, and that axial force will travel through the centroid of this member, and when it comes down here, that axial force can cause this to fail under yielding and rupture in this line perhaps. And then when you have yielding and rupture, the next limit state or failure mode that you could have would be the block shear that we already mentioned yesterday. So this can fall in block at the end, and you have holes, therefore bearing and tear out could also occur. Now you consider that the force is ready to travel through the bolts, and then the bolts can fail under shear because it's gonna have a shear plane, and then the force will go into the gusset plate, and the gusset plate also has holes, so therefore the gusset may fail under, and it's not gonna fail under rupture because it's big, but you can still have block shear on the gusset like this, and that block, and bearing tear out on the gusset plate, and when the force travels through here, and then it's gonna find the well, so we need to check the failure of the well, something like that. So that sort of sums up how we approach the design of the connection. You know the material, you would know the strength of this member, the strength of the bolts, the strength of the wells. You know that you need to transfer the axial force. You know the axial force travels from the central of the member through this part, through the bolts, through the gusset, and then through the welds. And we know how the force is going to cause some failure, as I already listed. So that's it, in a nutshell, the design of the connection. This is pretty much the same idea, how the force is transferred, but when it arrives here, it's just going to go partially this side and then partially that side, that's all. Okay, that is more of the same. Here, let me put the airplane mode on my phone. Okay. And this is likewise, but it's going to be a very popular connection. Some of the places they call that star connection because I don't know, it doesn't look like star, but I kind of like the details because you have a very heavy gusset plate here, and then you have the H-shaped member as a member that takes the axial force. This is heavy bracing. So we would try to connect the edge to the gusset by using 4 angles at the flange, right? Because the angle is 90 degrees, so in one of its leg, it will be connected to the flange, and because of the 90 degree that it possesses, another leg will be attached to the gusset, right? Maybe this picture would be better. I wonder why I didn't write anything on this book at all yesterday, so I'm gonna do it today. It's a bit hard to flip, but here, how about that? So if, it's gonna be too small, right? But anyway, let's try. Let's say if this is the flange of our edge, when you have the angle, it's gonna come like this, right? Oh, looks bigger. So you can bolt the angle to the flange like this, and then the gusset plate is going to be here. So then you can bolt it on another side, and then you have another angle coming in here with the bolts. And so we have 2 times the bolt on this side, but this bolt will have what we call the double shear. So the capacity is pretty much the same. Well, I think this is beautiful. This is how we utilize the angle. Okay, so this is the gusset, and they call this star bracing. And if it's not enough, we can also add the plate here to help transfer the force from the web of the edge shape as well. And remember yesterday, this edge shape now we connect through both the flanges and the web, so the member itself will not have the problem with the shear lag. So this is the perfect example. So if I don't have the plate at the web like this, we're gonna have to check the shear lag of this member. But for this detail, we don't have to. Okay? I think it's a bit too small, so I may stick to the piece of paper, right? So let's just come back to our academic side of things. Okay. Now let's get to know the first material that we use to connect the steel members together. First is the bolt, of course, and generally we can have more than two types. I think there is the third one available now, stronger than A490, but generally it's been used so far with the two types, A325 and A490. The number would indicate the strength associated with the bolt itself. So A490 is a bit stronger than A325. Now there is the letter denoted at the back to indicate where the shear plane is, because the bolt we have the thread like this. If the area of the failure is within the thread, you know that this thread portion has smaller area, right? We lose something when we create the thread. So the bolt under shear, if we're going to shear off the bolt at this portion, this is called the shank. The shank has area more than the thread. So if the shear plane is here, we're going to have more shear strength coming out of the bolt. But if the shear plane happens to be at the thread, you're going to have less strength because of less area. So we denote that at the end of the number by using X and N. Now X would stand for excluded. That means shear plane is excluded. The thread is excluded from the shear plane, meaning the shear plane is at the shank, stronger. Now N would stand for thread included. So that means the thread is, the shear plane is somewhere around here. So the N type would be weaker than the X type because the shear plane is at the thread. And we have less area. Okay? Now the question is, can we actually locate where the thread of the bolt will be under construction? The answer is yes. If we care to check, we can acquire the dimension of the bolt before we start the installation process. So we would know how long the shank is, we would know how long the thread is, and we would know how thick our materials will be, right? The thicknesses of all the plates and the flanges and the webs and everything. If we really want to know, we actually can. But if we don't want to know, or if we cannot obtain information about other related dimensions at all, I suggest you go with the N type because it's safer, right? It's going to be conservative, but it's the only thing we can do if we do not know where the thread actually is. Okay, so that's one thing. Now the next thing we should know is the size of the bolt itself. Generally, this is in the metric form. So we have the common types used in the market would be from M20 to M24, I suppose. You can use smaller than that. You can use bigger than that. And I believe we have bigger bolts than M36. But if you are going to use the unusual bolt size, please keep in mind that you may need to order it from abroad. It may become unavailable in the market, right? And one thing that we should do if we are going to design the bolted connection is that you should try to keep the bolt size just one size to try to avoid confusion in the installation process. Even if it's going to cost more in some cases, but you should just keep it to one size, right? So for example, if you decide to use M20, you should use it for the entire area for ease of construction and to avoid confusion. But let's hope that we can. It's not a rule that you have to strictly follow. It's just the way that we give details and make our work easier. Okay? And the next thing that we should know is that if you have the bolt, of course, the size of the hole should be bigger than the size of the bolt itself. Otherwise, people who erect the structure would praise our ancestor for having the hole size equal to the bolt size, because it would never fit. Anyway, generally the hole size will be slightly bigger than the bolt itself by 2 to 3 millimeters. And when we calculate the net area, remember we mentioned the net area that we need to consider because we lose some material due to the hole punching. We need to take more out of the size of the bowl plus 2 more millimeters. So you see, if we have M20, the whole size will be about 22 millimeters. And when we calculate the net area, we need to deduct it by 24 meters. 2 millimeter more from the whole size for every size of the bowl, as you can see. This is because of the damage on the surface from the hole punching process. That is why we need to deduct 2 millimeter more out of this. Okay, and for the type of installation, we have 2 types of bolts that will dictate the behavior of the force transfer. First is the typical bolt called the snug tight bolt. We're just gonna snug it, okay, by using the torque wrench. So that's a typical one, and if we use that one, the force transfer mechanism involved is the bearing force. So you remember bearing failure yesterday? If we install the bolt by using the snug tight, the force transfer will be via the mechanism of the pressure between the bolt and the plate. So let's say this is my bolt. Okay, it's just a bit crooked. And we have a plate here. Like this. That becomes a bolt. And if I apply tension like this, if I pull this to the left, that means this area will come into contact, right? On the right, between the bolts and the plate. And we're going to have a pressure here. And the pressure like this is what we call the bearing force. And the force we transfer because of the pressure between the contact surfaces, or the bearing force. And for this piece, it's going to be on this side, correct? So that's a bearing force. That is why we call it bearing type connection. That's why it is named the bearing type connection. It doesn't mean that it's going to fail due to bearing or it bears something. Okay? This is bolt, and that means when you look at this free body diagram, it means that your bolt is going to fail due to the shear force here, right? Another one is the slip critical. As the name suggests, the slip is critical, so we will not allow it to happen. So that type of the connection, we will apply the pre-tension force. And when we apply the pre-tension force, and when it wants to squeeze back, it's just like the pre-stress concept, the pre-tension force will create friction between the surface, like this. So the slip critical type of installation will use the friction mechanism to transfer the force from this piece to that piece. The major difference is this. You see that, right? Yeah, I know how to do it. Zoom out a little bit. Okay, how about that? So, for this, you can see that the mechanism for force transfer is bearing force or pressure. So that means deformation is inevitable. We're going to have deformation. All right? And this, we hope not to have deformation, because if you have deformation, it would mean that your connection slips. And the name is slip critical. We don't want slip to occur. So we are going to use this type of detail when we need to control deformation. So first, if you have the structure that will have to undergo the cyclic loading conditions such as earthquake, you're going to have to use this detail. Okay? Or if you have a very tall buildings, AISC would suggest the building taller than 100 feet. So that means about 30 meters something. If the building is taller than that, you're going to need this detail as well, because this bearing type connection will induce the, say, accumulate the deformation. So your building would start, to have a lot of deformation due to bearing deformation coming from the holes. So if the building is too tall and you use this, you're going to have the deformation from here, there, and everywhere. So in the end, it's going to be too much. And therefore, they suggest this. Okay? But in general, typical connection work, this is good enough. Okay. All right, so we come back here. Is there any question? Now, I already mentioned that. Okay. Now, the next business is the bolt holes. Generally, we would have to deal with the standard holes most of the time. And like I mentioned before, the size of the hole will basically equal to the bolt diameter plus 2 millimeters if your bolts are not bigger than M22. If it is from M24 onward, the size of the hole would be equal to bolt diameter plus 3 millimeters. Okay? If you think this is too much trouble, you can just memorize the plus 3 millimeters. 1 millimeter will not kill anyone. Right? And oversized hole will be a little bit bigger, so it's 8 millimeters. But if you use this, you cannot count that bolt in your bearing type connection, because your bolt hole will be too big and it will take very long before the bolt will come into contact with the plate or the flange or the wells for that matter. So the bearing mechanism will take very long to occur, so we cannot count that into our force transfer system. Okay? But from time to time, you may need to use this to help ease the installation process. Okay? And then we have the short and long slots, of course, to provide the movement for your connection. So, a roller, anyone? And next is, of course, the spacing. Now, generally, what we need to worry about is the minimum spacing between each bolt, because that will involve the installation process directly. If the spacing is too small, that means you cannot fit the torque wrench between the two bolts, and somebody is going to press you very, very highly for that action. So we need to at least provide the space no less than 2 plus 2/3 of the bolt diameter, or this is really the minimum requirement, but generally, who want to calculate that complicated number? So we engineers generally use 3 times bolt diameter. Okay? And generally, let's say in the US, they generally use 3/4, 7/8 inch, and 1 inch bolt diameter. Those are the 3 popular sizes used in the US. So if the biggest size is 1 inch, so they multiply that by 3, it becomes 3 inches. So the typical spacing used in the US becomes 3 inches. So generally, they would just, okay, if you have the spacing, they would stick with 3 inches. But keep in mind that it would work for up to, I don't know, if the bolt size becomes too big, 1 inch will not, 3 inches will not work as well. Now, for our business in Thailand, we don't have, that many. But I hope that I don't know, who knows in the future, because if the labor cost keeps increasing, and one day trying to build everything on concrete may not be very profitable anymore. So if we use steel that much, we may have the typical spacing that is generally used amongst engineers. But right now, I sort of myself use maybe M20, 22, 24, that sort of thing. So if you multiply 3 to 24, it's 7 centimeters something. It's a bit annoying, so I myself would go for 8 centimeters as my preference. But again, you can just use any numbers you are comfortable with, but make sure that it's gonna meet the minimum requirement. Okay, and the maximum size is concerned with the corrosion and painting stuff, but they say you don't have to use more than 30 centimeters spacing. So we're talking about a foot here. So I don't think that should be any concern for us at all. And just make sure that you provide enough minimum spacing for installation. That will be fine. Okay. Now, with all those gimmick aside, it's time to talk about the strength now. Okay. So generally, the bolts can carry tension and shear. So let's start with tension first. And if you can recall the picture that you just saw, we have the shank portion and we have the thread portion. So if you apply tension to the bolt, naturally it's going to have to fail at the thread because you have less area, right? So when we consider the strength of the bolt, this is the ultimate tensile strength of the bolt material, which is generally very high. But then the area of the bolt, we need to deduct the thread effect. So 25% will be taken off the area. Okay, but to help our calculation, it's not very convenient to multiply the area with 0.75 all the time, right? So they move 0.75 here and multiply with the ultimate tensile strength instead. So every time you design the bolt to carry tension, you can just use this F and T and then multiply by the area of the bolt right away without having to multiply with 0.75 all the time. That is why this is not FU, you see. It becomes FNT. It's a nominal tensile strength. You see the difference? This is not the true tensile strength. It's the calculated tensile strength because it is multiplied by 0.75. See the difference? We talked about nominal yesterday, the calculated strength, and that means, ladies and gentlemen, you can just plug the number from this table and multiply with the area of the bolt right away. You would have nominal tensile strength of the bolt because this is already nominal tensile strength. But don't forget that this is nominal, so you need to multiply with a fee and divide with the factor of safety before you have desired strength of the bolt. Okay? And ladies and gentlemen, this is the rupture mode because tension will tear your bolt into two pieces. So we have phi equal to 0.25 and factor of safety equal to 2. Basically, if one bolt can carry 10 tons of tension, we can only use 5. Okay? Now the shear. Again, when we talk about the shear, it means that we need to convert our tensile strength into shear strength by von Mies criteria. And I don't know why they use 0.625, but let's say it's 0.6. I got this number, I don't know, from the bolt design guy or the commentary of AIC. It's been a long time. So that's one, to change the ultimate tensile into shear. And then we have that, 0.9. It's called the bolt group factor. We need to have this bolt group factor because they are still a little bit afraid that if you have a lot of bolts and then you apply the shear force to them, how can you be sure that every bolt will carry the same amount of force? It's not possible, actually. Let's say if I have a connection that looks like this, and then I apply tension like that, you know. If I apply tension in this direction, that means the bolts will have to carry the shear force, right? And how can you be so sure that this bolt will carry the same amount of force as that one? Naturally, it's not possible. You know, the ones up front will have to take more, right? But when we design, we will just, okay, I will take the force and divide by the number of bolts because there's no other practical way to do it. And we could do that because the bolt group factor has been included in our design already. That 0.9, okay? So after multiplying the ultimate tensile strength with this von Mises and with 0.9, we have this as the nominal shear strength of the bolt. But this is for thread excluded or X type. If we have N type, it means that we also need to reduce the cross-sectional area of the bolt. So therefore, if you have the N type, you take this number and multiply further by 0.8. So you have this number for the N type. And after all the hullabaloo, you know, we have the numbers that you can use right away as the nominal shear strength of the bolt. You multiply this with the area, you have the nominal shear strength of one bolt in terms of force. But don't forget that we need the phi and factor of safety after that as well. Okay? And one more side note here, that is, if you have a very, very long connection, you need to reduce the value by 0.833 further because long time ago, the bolt group factor used to be 0.8. Now they increase it of late, but still, if it's too long, it's still not so sure about the strength. Okay, so you need to further reduce it if your connection is longer than, say, a meter, say 1 meter. Okay. Now, sum this up. We have equivalent bolts. We don't have to be so crazy about the A325 and A490. Listed here, you can have the A325M, basically in metric unit. You can have this F1852, the twist-off tension control. I've heard about this before. I have never seen the live one myself, but when you use the torque wrench and it's tight enough that the head's going to come off to let you know that, okay, you have applied enough torque and the installation process is now complete. It's pretty convenient. And then A354BC and then that sort of thing. Okay, there can be more than this. It's just example of the equivalent types of bolt. Okay, and if you want to know more about the bolts, you can read the RCSC. I don't know if this is the most up-to-date one, and the design guide about the bolt itself. Okay, all right. So far, so good, right? The bolt is so straightforward. And if you look at the specification, they will tell you that the design of the bolt can be done by just using one formula.